We are discussing the solutions for quiz 4. A block is moving in 2 dimensions on a straight line from 0, 0 to 2, negative 2. One of the forces is a constant force, 10 newtons, 3 newtons, applied throughout the entire motion. How much work is performed by the force on the block? So the work done by the force is F vector dotted with a vector delta R. F vector is 10, 3. Delta R is final minus initial. That's 2, negative 2. So F dot R is Fx times delta Rx plus Fy times delta Ry. So it's 10 times 2 plus 3 times negative 2. And that comes out to 14 joules. Next problem. We consider the graph with force versus position x, as shown. The hash mark on the vertical axis is 36 newtons. A 9.1 kilogram mass starts at rest at x equals 0 and is accelerated by this force. Find the velocity is 15 meters. Okay, the idea is we're going to calculate the work done by this force. Then we'll use the work energy principle to figure out the final kinetic energy that will tell us how fast it's going. Okay, so the work done by this force is just the integral of the force, this force. Okay, so we shouldn't say F0. There should really say plain old F, the area under the curve. So we have this triangle here. That's area is going to be 1/2 times 5 times the height, which is 36. And we have this block here, which is 5 times 36. We have this triangle, which is 1/2 5 times 36. That comes to 360 joules. And so now we have the work energy principle. Delta K is equal to the net work done, which is 360. So since we start from rest, the initial kinetic energy is 0, the final kinetic energy will be 360 joules. So we have 1/2 mv final squared, or 1/2 9.1 v final squared is equal to 360. Solve for v final, that will be 8.89 meters per second. Okay, we have this block. It's on the top of the inclined plane, height h. Inclined plane makes an angle of 30 degrees with the horizontal. Block starts to slide down the frictional surface and reaches a speed of v at the bottom. If the same block were to reach a speed of 3v at the bottom, it would need to slide down the frictionless inclined plane of what vertical height? Okay, so this is conservation of energy. Kf plus ui is equal to kf plus uf. So the initial kinetic energy is 0. The initial potential energy is mgh. The final kinetic energy, the final potential energy is equal to 0 because the height is 0, y is equal to 0. And so we can solve for the final kinetic energy is mgh. So we have 1/2 mv final squared, that's the kinetic energy, is equal to mgh. Solve for v final squared. V final squared is equal to 2gh. The m's have cancelled. So we get v final is equal to square root of 2gh. Now, if we make v final 3 times bigger, okay, then we're going to have that h is going to need to be, in order to make this 3 times bigger, we need h, because it's inside the square root, must be 9 times bigger, so we need 9h. Okay, so that's what we need. All right, next problem. We calculate the change in the potential energy of a 89.7 kilogram man when he takes an elevator from the first floor to the 38th floor, if the distance between floors is 4.05 meters. Okay, we're going from the first floor to the 38th floor. Okay, delta U is mg delta y. Delta y is from the 38 to 1, between 38 and 1, that's 37 floor differences, times 4.05, and that's 150 meters. So delta U is 89.7 times 9. That's the mass, 89.7 times g, which is 9.8 times 150, which is delta y. We get 1.32 times 10 to the 5th joules. Okay, an ideal spring is fixed at one end. A variable force F pulls on the spring. When the magnitude of F reaches a value of 37.8. The spring is stretched by 17.2 centimeters from its equilibrium strength. Calculate the additional work required by F to stretch the spring by an additional 12.5 centimeters from that position. Okay, so the spring force Fx is equal to minus Kx. So we're told that the value is 37.8, so negative 37.8 when x is equal to 0.172. So we can solve for k is equal to 220 newtons per meter. So we need to know the extra work that needs to be done. So we just need to calculate the extra potential energy that's going to be stored in the spring if we stretch it this additional amount. So it'll be 1/2 kx final squared minus 1/2 k initial squared, because the work you will do will go into storing this energy as potential energy. So we'll have 1/2 220 for k. The final stretch will be, it's an additional 0.125 meters, so 12.5 centimeters is 0.125 meters, but you add this to the 0.172 meters that it has already stretched, so that's x final. You square that, and then we have minus 1/2 220 times x initial, which is 0.172 squared. And the difference of these potential energies is 6.45 joules, and so that's the additional work required. A child, 25 kilograms, slides down the long slide in the playground. She starts from at a height of 22 meters. When she's partway down the slide at a height of 10 meters, she's moving at a speed of 8.10 meters per second. So let's take this to be y equals to 0. Calculate the mechanical energy lost due to friction. Okay, the work done by friction, or the non-conservative force, is the change in the total energy with delta K plus delta U. That's the total change. That's the change in the total energy, so we take each part delta K and delta U. So K final minus K initial plus U final minus U initial. So K final is 1/2 mv squared, so 25 is the mass. The final speed is 8.1. K initial starts from rest, so it's 0. And U final is going to be mg y final. So we have 25 times 9.8 times 10 is the final height. That's what it says here. And so for the U initial is 25, the mass, 9.8 g times 22 is the initial height. Okay, so we get the work done. The non-conservative force is negative 2.12 times 10 to the third joules. So 2.12 times 10 to the third joules lost. A 67 kilogram human sprinter can accelerate from s to 10 meters per second in 2.1 seconds. What is the sprinter's average power output? Okay, the work done by the net force is the change in the kinetic energy. That's 1/2 67 is the mass. V squared final. V final squared is 10 squared minus the initial kinetic energy, which is 0. That is 3.35 times 10 to the third joules. So that's the net work done divided by the time to get the power. 2.1 is the time. So we get 1.60 times 10 to the third watts. Next problem, number 8. It takes a minimum distance of 48.96 meters to stop a car moving at 12.0 meters per second by applying the brakes. Assume that the same frictional forces apply. Find the minimum stopping distance when the car is moving at 26.0 meters per second. Okay, the work done by the net force is equal to the change in the kinetic energy. So what we're going to do is we're going to figure out the net work done. So V initial is equal to 12 meters per second. The final kinetic energy is 0 because it stops. So the change in the change in the kinetic energy is 0 minus 1/2 m times V initial, which is 12 squared. And so that comes out to 72 times m. This m is not meters. This m is actually for the mass. Now we switch to the case V initial is 26 meters per second. So in this case we have 0, which is the final kinetic energy, minus 1/2 m26 squared. We get negative 338 times m. So the ratio of these network done, the network done in each case will be 333 divided by 72. That's 4.69. So it's 4.69 times the amount of work. So now, if the force is the same, then because work is force times distance, we need 4.69 times the distance. So 4.69 times the original distance, 48.96, That comes to 2.30 times 10 to the 2 meters. Let's go to the ninth problem. A small block of mass 1.10 slides without friction along the loop-to-loop diagram, loop-to-loop track shown. The block starts from point P at a distance 60 meters above the bottom of the loop. Okay, this distance is 60 meters, and the loop radius is 18 meters. What is the kinetic energy of the mass of the point 8 on the loop? Okay, so this height is 2r, which is 36 meters. Conservation of energy, K initial plus U initial is equal to K final plus U final. It starts from rest. This was not clearly stated, but we announced this in class. And so we have U initial is equal to mgh, so 1.10 times 9.8. And so now we have U final is going to be 1.10, the mass times 9.8 times 36. Okay, so now we can get K final, that ends up being 259 joules. Last problem. A car is moving at speed 12 meters per second and hits a parked car. Both cars move together. If each car has mass 1,500 kilograms, how much kinetic energy is lost in the equation? So first we have conservation of momentum. So we have the initial momentum coming from this car. This is starting from rest. So the initial momentum will be m times 12, where m is the mass, which is unknown. Now the final momentum, the final case, we have both cars stuck together with a mass 2m, moving with the final velocity v final. So we have 2m times v final. So m times 12 is equal to 2m times v final. We can solve for v final. That's 6.0 meters per second. Now the initial kinetic energy is 1/2 the mass of this car. It's 1,500 times the initial speed, 12 squared. That's 1.08 times 10 to the joules. For the final kinetic energy, we have both cars moving together, so the mass is 3,000, and the speed is 6 meters per second, so 6.0 squared. And this is 5.4 times 10 to the 4 joules. The difference in the kinetic energies comes out to be negative 5.4 times 10 to the 4th joules.